Thanks everybody for joining this, webinar of Galea and kind of the latest capabilities and some of the things we've been working on. My name is Joseph Artuso. I'm the Chief Commercial Officer at OpenBCI. Also joined by Ava Esteban, one of our software engineers, and Connor Rusumano, our CEO, wearing a headset. So today we're going to walk through a couple different things. We're going to show, just kind of an overview of the device itself. This might be a bit of a repeat for some of the people that are already familiar, but it's sort of a good starting point. And then we'll jump into Unity to show you how some of the sensor data can be accessed within Unity. We'll go over, kind of what we're calling like the virtual technician, or some recommendations about how to adjust the headset fit that can be kind of dynamically made based on the sensor data in Unity, which is great. And then show off a couple other, projects and integrations that we have before transitioning to a Q&A.
That's right.
So on that front, if you have questions, we're going to try and, I'll be monitoring the Zoom, Q&A widget. If you look down in the bottom, there you go. I see Alex just asked our first question. So you can ask questions there. If you see a question that you also want answered, you can give it a little thumbs up. And then we'll try and answer the most popular questions either, during the presentation itself or at the end. So we'll do that. We'll try and pull some things from the chat as well, but it's actually much easier if you keep it in the Q&A for us. If you like what you see and are interested in learning more about Galea, you can go to galea.co. There's actually a sort of inquire form if you wanted to set up one-on-one time to discuss it with us. Ask you to just complete some information about what your interest is, and someone from the team would get back to you, or you can learn a bit more about the project through the website and through some of the other information we have. And on that note, I think I'll hand it off to Ava and Connor. They can give you a sort of overview of the device, its sensors, and some of the data that you're seeing on the screen at the moment.
Hi, everyone.
Hello.
Thank you for joining this webinar. Welcome to OpenBCI webinar number 2. So to start, we're going to give you an overview of the different data types that you can obtain using Galea. We already did this, like you mentioned in the last webinar, but we're going to show it again because there's a lot of new people joining. So you can see my screen right now, which is showing the OpenBCI GUI connected currently to the unit that Connor is wearing. So when you first open the GUI, I'm going to put it back to default. When you first open the GUI, the first widget that pops up is the signal quality test widget. This one gives you an indication of whether the channels are making good contact with your skin or not. So right now, most of the channels are blue, which means that they're not railed. And that means that the signal quality is good on his face. He has a couple of yellow channels, but the data looks okay. So we're going to keep moving with those ones.
If I could just pause there, because this will be relevant for later in the presentation, but here you can see that channels 7 and 8 are near railed, which is why they're appearing as yellow. The microvolt values, though, the actual physical unit that we're measuring is looking to be acceptable, under about 40 microvolt or UV-RMS. This railed percentage is just how close we're getting to the maximum limit of the ADC. And so we actually have the ability, if these do start approaching the rail, we have the ability to stop the data stream and come into hardware settings to change the gain. So I can actually just demonstrate this right now. If I want to get them farther away from the rail, I'm going to switch this to 6. So I'm going to cut that gain in half. And then I'm going to send this to the device. So right now I'm actually doing a live, I'm adjusting the registers of the hardware, or I'm adjusting the settings of the hardware in real time from the software. So let's send this and hopefully everything goes smoothly. So now if I return to the data stream,
nice.
You'll notice that channels 7 and 8, which were near railed before, they were around floating between 70 and 80%. As expected, because we cut the gain in half, those percentage values have also decreased by about 50%. So now we're no longer close to that rail.
Yeah, so using rail calculations is one of the ways that you can check if the signal quality is good. Another measurement that we use for that is the impedance of every channel. So if you go to mode on the top right of the widget and then select impedance, you can run an impedance check across each channel on the face interface to check whether the contact with the skin is good. So we've set different thresholds for the impedance measurement that we want. Below 750 kilo ohms, we deem it to be a good connection. Between 750 and 2500, it's okay. And if it's above 2500, then the impedance is too high and you should move the headset a little bit until it lowers, which means that the electrode is making better contact with your skin. So right now, Connor just ran the test and we can see that all the channels are green. That's great. They all have a low impedance. And so we can move on to have a look at some of the data.
Cool. And another just little kind of, I guess, additional comment there is that at this point, the impedance test only works for our passive electrode system, which is in the face interface. The harness here that holds the headset on the scalp, this has the 8 active EEG electrodes in it, and those active EEG electrodes at this point in time prevent us from doing an impedance check, though we're working on a new hardware solution that will allow us to run the impedance check on active electrodes as well.
Yeah. So I think we can first show the auxiliary data and then we can show like EMG, EEG, EOG, etc. So if you look on the top right, the Galea aux widget shows the battery of the device. Bottom right, sorry. If you look on the bottom right, the Galea auxiliary widget shows first the battery of the device and then the PPG data, which is the heart rate sensor, and the EDA, which stands for electrodermal activity, which measures the conductance of your skin, which will change depending on whether you're sweating. So maybe getting a little bit nervous or stressed. So if you look at the PPG lines, you can clearly see the heart rate.
Each of these, so here you can see, especially when I drink a lot of caffeine, occasionally my heart will kind of skip a beat. But for the most part, you can see this kind of consistent cadence, the peaks and troughs of my heart. And right now we're working on doing some derivative metrics. So looking at extracting SpO2 and other, heart rate variability from this raw data. And hopefully next time we have some updates for you on that front.
One of the lines is showing infrared and the other one is showing the red component. And at the bottom, you can see the EDA. Right now, it looks pretty stable. Mm-hmm. So if Connor, for example, pinches himself,
let's go for it.
It'll start increasing, as you can see, and then go back to normal again.
So I just pinched myself again.
So he just pinched himself again. So like pinching yourself or getting a little bit nervous will make the EDA go up.
All right, let's try it again.
Nice.
Yeah, it works pretty well. I mean, there is a little bit, there's like a 1 second delay, but that's actually, it makes sense because there is a latency or a delay of the sweat building on your skin after you've been, kind of after something's captured your attention or you've been kind of aroused in some way. We'll do it again. There it goes.
Nice. Cool. Yeah, so it's pretty responsive.
Yep.
So that's an overview of some of the auxiliary data. In terms of EMG, EEG, EOG, if you look at the signal quality widget, you can see, I don't know if the zoom quality is good enough to see, but each channel has a number. And the number on the channel corresponds to the number on the time series widget on the left of the screen.
Yep.
So if you looking at the face interface to start, channels.
1, 2, 3, 4. We'll start with this.
Yeah, 1, 2, 3, and 4 are EMG. So 1 is the left cheek, 2 is the right cheek, 3 is above the left eyebrow, and 4 is above the right eyebrow.
Mm-hmm.
And you can see them on the left side. Right now we're visualizing the data with some filters we've applied, like a notch filter for 50 and 60 Hertz. So if you open let's open the EMG widget. I
Gotcha.
think. We also have an EMG widget, which processes the data and normalizes it within the window interval that you choose and the minimum and maximum values that you set. Nice.
Cool.
So, okay, we're gonna do a short demonstration of how to trigger some of the EMG channels. So if you smirk left and then smirk right, we will be able to see the spikes in the left cheek and right cheek channels. So you can see them very clearly both in the time series widget and also in the EMG widget normalized. So when he's smirking left, it goes up to 1 and then right goes up to 1. He can do the same sort of movement with the left and right eyebrows. Can you try 3 and then 4, 3, 4, 3. So that's left eyebrow raise, right eyebrow raise, left eyebrow raise, right eyebrow raise.
All right, let's do the mini game again so everybody knows I'm not cheating.
So Connor is leaving his controller on the table, and I'm gonna call out a number, and he has to flex the muscle that corresponds to that channel. So let's start. 1, nice. 3, 2, 1, 4.
Hang on. Wait for
That one
it.
is hard.
There it is.
Nice. 2, 1, 3, 4. Nice.
Gotta work on
4
that
is
one.
the hardest one for you,
Definitely.
but I can see it. 1, 3, 4, 2. So you can see that he has a pretty good control over the 4 channels.
Cool.
Cool.
That worked well.
Nice. So I think next we will show you some of the EOG data from the face interface.
Oh yeah.
So EOG stands for electrocrylography. And we have 2 channels for this. Can you open the signal quality widget again?
Yep.
So if you look in the signal quality widget, we have a vertical EOG channel, channel 5, and then a horizontal EOG channel across the face, which is channel 6. And to visualize the data properly, we have to disable the filter. So I'm just gonna go ahead and do that.
While you're doing that, I'll just explain for those of you that don't know, your eyeball it has a field, an electric field. And so the way this works is we're taking a voltage measurement or a potential measurement across, from opposite sides of the eyeball, both horizontally and vertically. And so as you're looking left and right, we can actually see the shift in the angle of the eyeball as that field, the orientation of that electric field is changing. And so essentially EOG is electrical eye tracking, which is, obviously an extra data set that we're adding to the image-based eye tracking that's going to be in the Varjo headset, or that is in the Varjo Aero headset. But having those 2 data sets together, the EOG and the image-based eye tracking, will help us really validate and confirm the efficacy of both data sets by combining them together.
Okay, thanks for explaining that. I disabled the filters.
Cool.
So right now we're seeing raw data on channel 5 and 6. Can you start looking up and down, up, down? So as he looks up and then down, we can see the movement very clearly in channel 5, which is the vertical EOG. A little bit bleeds into channel 6 horizontal, which makes sense, but channel 5 is the main one to detect up and down movements. And now if you do the same, but left, right, eye movements, we also see that in channel 6.
That one's very clear.
Yeah, we can also do a combined movement, like if you look to the top right, bottom left.
I have a theory as to why the horizontal looks better than the vertical, because mechanically the horizontal electrodes are perfectly aligned through the axis of my eyeball, but channel 5 is actually not perfectly vertical. you can even see it on this diagram. Channel 5P is not perfectly vertical above 5N. So there actually is an angled orientation of that measurement, which I think is part of the reason the horizontal looks much more clean than the vertical. So it's a theory, but we're improving that with the beta hardware design, is better aligning channel 5 vertically.
Yeah.
There's actually a couple questions that maybe you can touch on. One was, why did we choose to do some active electrodes and some passive? Or, maybe explain which electrodes are active and which ones are passive. And yeah.
I mean, we haven't shown EEG yet. Maybe I can quickly go over it, but later.
Cool.
Well, I think when we show passive and active EEG, it'll be better to answer this question.
I can quickly touch on the theory behind this, but basically the data that we're collecting from the face is much higher in amplitude. Like when you're measuring EMG or EEG, it's technically the same physical unit. It's voltage over time. You're looking at shifts in potential over a window of time. With anything generated on the face, the strength of that signal, because it's most likely coming from a muscle or even the eyes, is 10 to 1,000 times stronger than an EEG signal. And so as a result, the active amplifier on the face would actually be overkill in many cases because the signal is so strong already. The one exception here and kind of a gray area is channels 7 and 8, which actually are passive EEG channels. There are only passive EEG channels, but they're integrated into the face interface. So we stuck with the same, the same kind of non-active solution for that entire suite of sensors, or that entire collection of sensors. And additionally, the active electrodes on the back, most of the time, unless you're bald or you have very little hair, you're going to have to sample that data through hair, which is an additional obstacle. And so for that reason, because we have, even more challenges in kind of getting a clean signal, we felt that amplifying the electrodes from the scalp, the ones that are pulling data through hair, would be a good solution.
Great, thank you.
Yeah.
So
I think
adding to that, if we show the hardware settings later, or I don't know if you got a chance to see earlier when Connor opened them.
Let's do it.
The gain that we are setting by default for the passive EEG is right now higher than for the active.
It's a little small on the screen share, I think, but yeah, we have the ability to configure the passive versus the active electrodes differently.
If I do this, do people see it better?
Like
if I lean in and you guys are screen sharing?
No, it's
Okay.
I'm sharing the screen directly, so they see my monitor.
All right, I'm going to start the data stream again, but yeah, and so cool.
I'm going to put the filters again back on.
Great.
Yeah, so we have the active electrodes set to the minimum gain. We don't really need to increase the gain for them, and we get pretty good data, whereas for the passive, we've increased it a little bit. Okay, so the filters are, did you have another question, Joe, or should I carry on?
There's kind of a general question about how, how sensitive all of the electrodes are to movement. I'm not sure if we can incorporate that into what we have planned today. Might be good for a future session or recording, but keep that in mind as you continue to go through.
Great.
Okay. Let's show some of the, let's show some blinks on the passive EEG actually. Okay. So passive EEG channels, like Connor mentioned, are 7 and 8. And those are located on the forehead. They're very good for detecting blinks, for example. So if you blink in blocks of 5, you can see them in the time series very clearly. Nice. So he just blinked like 5 times. And you can also see the blinks in some of the active channels because he's flexing his face, especially in 9 and 10, because those are closer to the face. They're the ones on the front of the midline. but 7 and 8 are the best channels to visualize this.
Yep.
Let's open the Fourier transform, I think.
Right.
And band power widget. So these are two widgets that we use to visualize EEG data. The one on the bottom is a fast Fourier transform plot, which shows you the frequency spectrum of the signals. And the one on the top is a band power calculation. Nice. Okay. So one of the tests that we run for EEG data usually is producing alpha waves. So alpha is the frequency band that goes from 8 to 13 hertz. And when a person closes their eyes and relaxes, usually that frequency band will peak.
Just bring up the spectrogram.
Yeah, good idea. Can you hide 7 and 8 from the time series? I think that would.
Sure. Or just take them out of here completely.
Yeah.
Got it.
So that it makes the signals a bit bigger.
Cool.
So Connor also opened up the spectrogram, which is really, it provides a nice visualization of
I'm gonna
the
bring max
frequencies.
frequency into 20. I don't think we're looking at anything above 20.
Cool. So on the spectrogram right now, on the top, we have channels 9 through 16, which are the active electrodes. And in the bottom, it's EMG and EOG data. The active electrodes, like you could see it earlier in the signal quality widget, but they are located on the midline and the back of the head, the occipital region. Let's try to make some alpha. So right now, Connor has his, I can tell he just closed his eyes because his alpha power band is peaking above the rest. And also, if you look at the Fourier transform, the frequency spectrum, you can see a big peak that goes up until 10 UV or even higher at around 10 hertz. So the frequency of the peak will change a bit depending on the person, but it's usually in the range of 8 to 13 hertz. Can you open your eyes? So now he opened his eyes and all the bands are back to being more or less the same. So alpha is not peaking anymore. And if we look at the spectrogram, you can see a clear increase at around, yeah, like 11 hertz.
Yep. So this line here, this one that's kind of, it goes into green and yellow, and then this deeper red. You know, here are the periods in the yellow and especially in the red where I had a very high amplitude alpha. So, you know, that's when it was peaking at the strongest amplitude with my eyes closed.
Yeah, you had some clear alpha. It's also possible to see the alpha waves in the time series. And if you count the oscillations, you get yeah, it'll be around 11 hertz frequency. I don't know if it's too small to see on the Zoom.
Actually, yeah, could we, let's do that. What I want to do is I'll turn off 9, 10. So we'll keep 11, 12, and then really 15, 16 are probably, these ones are the ones that if you look here, let's go signal quality. So 11, 12, 15, 16 are the ones that are kind of arrayed across the visual cortex. So this is where we should see the strongest presence of alpha. So I'll turn them off here too.
Yeah.
And so I'll try and do that again. And actually, if you could, if you see the distinct waveform in the time series, especially, let's pause because this is a pretty cool instructional moment.
Yeah. Oh, I need control of the mouse. Yes. Okay. I paused it.
All right, cool.
Nice.
So this is, all right, so now what we can do here, you know, this is, if you're not familiar with brainwaves, this is probably the clearest demonstration of how to assemble, or I guess kind of diagnose a brainwave. But here, if we look, I don't know, can you see my cursor still?
Yeah.
Okay, there it is. So let's go here between, you know, T-3 and T-2, or rather T+3 and T+2 seconds. So if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Between t+3 and t+2 seconds, we count about 11 waveforms. And what you'll notice is that if we come down to the FFT plot, the peak or where you see this kind of camel hump in the curve is around 11 hertz. And so this, this right here is or each one of these is brain waves, and this brain wave is the alpha frequency, or the alpha band, I should say, which we have set to between, I think, 8 and 12 hertz. So any data that's coming in at between 8 and 12 hertz gets bumped into or categorized into, or 8 to 13 hertz, I should say, into alpha. 13. So all this data here in the 8 to 13 hertz range is why we see this peak in the band power widget over here. And why you also see at about 11 hertz in the spectrogram, a strong presence of alpha in the last, 5 to 10 seconds here. Cool.
Nice. Okay. Let's change the layout to be 3 widgets again.
Okay.
I think. Nice. So that's EEG data. We have a few more widgets, like, can you open the drop down?
Mm-hmm.
For example, the networking widget, and also we have the packet loss widget that you can open if you want.
Yep.
All of the data from the different widgets can be streamed out of the GUI in real time by using the networking widget. So if you open it, So the networking widget allows you to use different protocols. We have serial, LSL, which is lab streaming layer, UDP, and OSC options available. And you can basically select the data if you open the drop down. Thank you. You can basically select the data from any of the other widgets and a couple more additional calculations that we've added, and start streaming it out in real time, and then catch the stream with a different applications such as Unity, Unreal Engine, MATLAB, whatever you want to use. In the last webinar, we showed you a couple games that we've developed in Unity using UDP. So for those games, we were streaming EMG data out of the GUI using the networking widget, and then catching the stream in Unity and playing a game similar to Temple Run, where you control that cat running through the city. I don't know if we want to show that in this.
Let's do it, I'd say, afterwards. Let's demo. The big thing that we want to show off this time is that we're starting to make progress on the SDK side to cut the GUI out as a necessary kind of middleware to be getting processed, filtered, and data directly from the Galea device into Unity or other game engines or 3D engines. And so what we've started to do is kind of strip down the GUI into its fundamental kind of backend data blocks, if you will, and started porting a lot of that stuff directly into Unity using BrainFlow, as our kind of underlying SDK. But the great thing is that over the coming year, we're going to be porting a lot of the functionality and the utility that's in the GUI directly into the VR experience that I'm currently inside of. So you won't necessarily need the GUI running secondhand or kind of in the background to be validating signal quality and doing basic filtering and data routing.
Great. So yeah, like Connor explained in the last webinar, we showed you how to use the GUI, and now I'm gonna close the GUI and show you one of the applications that the OpenBCI has been working on.
I think you can leave it running. Like the GUI, we should be able to stop the session, I think, and then because then we can just fire it back up again. At the end, I think after we do this demo, we can demo what we showed last time.
Nice.
So cool. Can I give a little intro on this?
Yeah.
So doing this whole thing, building headsets for measuring physiological data and psychological data, it's an extremely tough engineering challenge. One thing that we've learned over the last 8 years is that probably the single greatest challenge or the single biggest obstacle is figuring out how to get a single headset design to adapt to different head sizes and shapes. This is the reality of kind of figuring out how to make a single system one size fits all, or having an adjustable headset that is easy enough to adjust, where you don't have 10 different levers and knobs and dials that each have to be precisely adjusted. Ideally, the best case scenario would be a single dial or a single knob that all you had to do was twist that one dial or that one knob, and it adjusted the headset perfectly to create the exactly precise amount of pressure that you want through each electrode to make good contact. Obviously, that ideal situation is not 100% realistic. And so, what we have kind of determined is that while we are making great steps, and we've got amazing engineers and designers working on the problem of neuroergonomics and designing a headset that's easy to adjust and fits a wide range of both adult and hopefully even child-sized heads. What we've learned is that what's really, really important is the actual the step of putting on the headset and adjusting the headset. And so one of the tools that we're working on internally is a instructional guide from within VR that essentially teaches you or shows a new time Galea user how to adjust the headset in real time. And this tool is going to provide real-time feedback in VR based on the signal quality of different sensors. And so it's going to propose different steps or techniques to adjust the headset based on the signal quality of the sensors within the headset. So, the picture's worth 1,000 words, the demo's worth 1 billion. Why don't we just get into it? And we can show you kind of where we're at with the proof of concept of having a VR instructional video that would help you adjust and connect your own Galea headset without having a technician or someone that needed to be around to help you set it up.
So I just started running the demo. You can currently see my Unity editor with the demo running. So I'm gonna give a brief overview of the editor, and then I'll maximize the game window so that you can see what Connor is seeing in VR. But basically, right now we are streaming data from the device and using BrainFlow to get the data directly into Unity. And on the right of the screen, you can see different parameters. So for example, the line noise type gives me an option to select, to select different filter options. Right now I have the 50 and 60 notch hertz filter applied. This is the same filter that you saw me earlier disable and re-enable when I was showing EOG data. And I can also choose a window size for the algorithm. And I have access to see different band power data. So for example, delta, theta, alpha, beta, gamma values. I can expand the drop downs and see the value change in real time, which is the same value that you were visualizing in the GUI earlier. There's also a couple more metrics like mindfulness and restfulness. These are the output of some machine learning models that we've been training to detect different mind states. And I think what I'm gonna do is maximize, about railed as well. So if you look in the bottom, you can see there's different railed thresholds that I can set. So like Connor was explaining earlier, when a channel is railed, it means that it's outside the range of what the ADC that we're using is expecting the signal to be. And so this demo focuses mostly on showing you the different railed state of the channels. And we've added the option of changing the threshold in case you want to make it lower or higher. So if you press, I'm going to maximize the experience. If you press A on the controller.
I'll jump in here for a sec because the initial state is actually just scanning live. So now we're going in, and this is the V0 of our real-time digital assistant, if you will. So the goal here is obviously to take out the, the need for a technician who has the knowledge of putting the headset on. But so right now you can see that as I look over here, can you guys all see what I'm seeing?
Yeah, they can see.
So it's showing me right now that the bottom of my face pad is all green, but the top of my face pad has a couple red and yellow nodes. And so what it's telling me to do is it's telling me to shift the headset up to put more pressure on the electrodes that are at the top of my face. So let's see if we can actually get this to work in real time. If I actually tighten that and I switch this down a little bit, maybe, hopefully I can actually deactivate that recommendation if I get the sensors to connect correctly. So, keep in mind that this is a V1, but the idea here is to provide helpful feedback in the headset assembly. So actually, or headset setup. So what I actually want to do now is I want to take the ear clip off, which may take a second for, oh, so this is cool. In this situation right now, it's telling me that node 9, which is at the front of my Mohawk, is not connected correctly. So it's asking me to slide the Mohawk down to make sure that that electrode connects better. So let's try and actually follow the instruction and see if it works. So let me get that one on and see if it turns green. Hey, look at that. So that was a perfect example of it doing what we want it to do, which is identifying an electrode that's not connected correctly and then giving the right instruction. So that was actually very cool. So now I'm going to try and do the same thing again to get these top ones to be connected better. So let me just kind of slide that into place. And this is where we may want to actually tweak the thresholds, because those electrodes, those yellow ones especially, are the ones that are telling the system to adjust itself, or telling me to adjust the systems, but they might actually be okay. So we do have some tuning to do. But why don't now I'm going to actually take off the ear clips, and let's see if the system notices that I've taken off the ear clips. This may actually take 10 or 15 seconds for, there you go. Check that out. So like I took the ear clips off, and now my active electrodes, because the system is no longer grounded into my body, those waves have or rather those signals have the potential to DC drift away from, my kind of electrical ground plane, which is why, it took 5 seconds or so, but now those signals are way, way off, and the headset knows that I need to reattach the ear clips. So let's see if I can do that. And let's see if it notices that the ear clips have been reattached. Nice. Cool. And so now it's noticing that initial diagnostic, which is the top of the headband, which we may just actually have to tune this because it feels like it's on pretty good. See if I can get it. This would be a big win if I can get this one on. I'm going to call yellow a win. We're going to call yellow a win for right now.
Yeah.
So that's pretty cool. Not bad for a first live demo. So hopefully, obviously this is going to evolve a lot, especially as the headset design changes. The mechanisms and the recommendations for adjustment are going to be updated as well. But this is, we believe that this is going to be really, really helpful, for using Galea in the wild, especially as more units get rolled out and we start to find applications for the device. Cool. Were there any more that we wanted to show, or any other demonstrations within this? Maybe try some of the other recommendations. We have them pre-programmed. So I think we're good.
I think we showed
That worked really well.
most of them.
Cool.
Cool.
All right, well, I'm going to close that back up. Bye-bye.
Nice. I'll minimize.
So how are we doing on time?
Well, let me check. 1:42.
1:42, great.
We could show the iMotions integration, or we could show Cut Runner first.
Let's do the iMotions integration because that's new. And then if we've got extra time, we can go back to the Cat Runner and Synesthesia Room before doing the Q&A.
Yeah, there were a couple questions about LSL, and I think that's relevant for the iMotion stuff because that's how we're currently using LSL streams to integrate with other software that supports it, like iMotions. So we went through that process recently.
So I'm gonna walk you, I can just walk actually through how to connect to iMotions. So iMotions is a high-end platform that allows you to analyze and to read from different biosensors, analyze the data, and integrate different biometric data, like for example, eye tracking, EEG, EMG, GSR, etc. And we've been working to integrate our equipment with it. So right now we can successfully read data from Galea with iMotions. And the pipeline that we've set up for that uses LSL, like Joe mentioned. So the first step is to connect Galea to the GUI again. So I have it open. Let me grab the IP. Yeah.
Cool.
So we're back in the GUI. And Connor can see the GUI in VR as well. And so I'm gonna show time series data, which is the 16 channels on the left. So the first thing is to open the networking widget. And then as the protocol, I'm gonna select LSL. For data type in stream 1, I'm gonna select time series. And I'll turn the filters on and start the LSL stream. And then I go to the iMotions software. And I think it's preferences, sensor settings. So we already set it up yesterday, but we basically made a profile for the Galea device and then search for existing LSL streams. So it found one, which is the one that I'm outputting from the GUI. And I selected it and I can save the settings. And if you look on the bottom, it says that it's first connecting, now collecting. Visualize it.
Hey.
So on the screen, you can see the data coming in from the different channels for Galea. It's labeled 0 to 15, but it's basically 1 to 16 in the GUI.
Nice.
Yeah, so those of you who are familiar with iMotions, seems like some of you've worked with it before, we'll have, because we're integrating with them through LSL, it opens up a lot of other opportunities with other software providers or software tools that use that as a protocol to access Galea's data. Connor and Ava, there's actually, I think this might be a good time to touch on a couple there's 2 different questions kind of around markers for the data that we collect. So there's one question whether, let me see. There's one that's like, is there a, actually just a general question, can you set event markers during an experiment or when replaying a recording?
This is a great question.
Good question. So BrainFlow right now has the option to add event markers to the data. So if you're integrating directly using BrainFlow with Unity, you could access that functionality and add it to your experiments. In terms of the GUI,
we don't have any
we
widgets
don't
for
have
adding markers within the GUI, but it's something that we've talked about for a long time.
yeah, it might be good to know if people want this, and then we can add a widget to the GUI that can do it.
I think what's also going to be really interesting and something that we're working on is having the ability in Unity and Unreal to script objects of interest or interaction logic into game objects, where we can programmatically identify when a Galea user has interacted with an object, whether they've touched it or grabbed it with their hand or controller, or whether they've looked at it with the image-based eye tracking, and then flagging the data that's being recorded with these kind of event markers that are programmatically integrated into the VR experience. So this is something that we're putting a lot of thought into now, which is like, how do we automate a lot of this stuff? As a developer, if you're creating a VR experience, or if you're creating an experiment in Unity or in VR or another 3D engine, how do we automate a lot of that kind of marker and kind of epoch binning, if you will, around the kind of the before, during, and after interactions within a game experience.
iMotions is also one of the softwares that we are integrating with. We're also looking at other softwares, and if you guys have suggestions of software applications that you would like to use with Galea, just type them in the chat. I think it'll be good to have some suggestions of what softwares we can integrate with it.
Yeah, we'll actually be following up with, a survey for anyone that attended, both to ask for topics for future webinars and, other integrations or demonstrations on the software side that would be interesting. Another related question from John Griffiths. Is there an accessible spare channel that could be used to capture triggers, from other sources marking events, for example, a TTL pulse or an analog signal? I think not for Galea, but maybe I'm wrong. Connor?
Yeah, go for it.
We don't have one for Galea currently, but it is something that we've been discussing for the next hardware version of the device. It's something that you can do with like the Cyton and the Ganglion and some of our other boards.
Yep, I think for beta, we may or may not expose this as part of the functionality of the Galea device, but on the PCBs, we will have the ability to interface or have kind of a GPIO or auxiliary input and output capability. And so the short answer is yes. We're striving to have that be part of the product experience.
Yep.
Okay. So we've got several other questions. We could use that time, or you could kind of go through one more thing before we transition to the Q&A portion. I don't know if you guys, what else we got?
If we have time, I think it'll be good to quickly show CAD Runner for the people who didn't join the last webinar.
Mm-hmm.
Yeah, why don't we do that? And then we'll give everybody a chance to go through the questions that are in the Q&A. Q&A window, upvote, thumbs up the ones that you want to see answered, and then ask any new ones that you want to get to in the next 20 minutes or so.
Oh, it's UDP. Okay. So I'm just gonna quickly run one of our demos that uses the networking widget in the GUI to get the data, as opposed to BrainFlow, which is what we showed earlier with the adjustment instructions for the headset. So Connor just opened the EMG widget and then changed the protocol to UDP and the data type to EMG. So I'm gonna go ahead and start the UDP stream and then launch our game. Oh, I think you grabbed yours. It's okay. It's loading. It takes a couple seconds.
I'm updating my settings.
Oh, maybe you can give a short explanation about the parameters while it loads. How to adjust them.
Sure. So this is at least a quite rudimentary mapping. Like we're actually for this demo only using 2 of the 16 EXG channels. But I think one of the big use cases or interesting use cases of Galea is looking at the motor function around the face and the scalp for new types of real-time input or interaction. I'm a big believer in using motor function and EMG for real-time interaction and using EEG and other stuff for the more passive opportunistic sensing. But in this demo, we have a pretty straightforward mapping between the EMG on my face to the control of a character in a game. And I think, obviously this could be used for games, but this technology could also be very, very valuable for individuals with motor disability who are looking for, further autonomy or more control over digital interfaces. So let's, without further ado, jump in and let's play this game.
Let me just pull up the VR view for them.
Cool.
Right now they're seeing the GUI. So I'll move the GUI to the other screen. And then
Am I in? Are they in?
they are in. So right
absolutely.
now, what you can see is Connor's VR view. He left his controller
Oh, there it goes.
and he's using his left and right cheek to control the lane that the cat is running in and trying to collect all the tokens and avoid the rats and the other obstacles. Nice.
So yeah, this is one example of us using the EMG data from the face, as a button and integrating it into a Unity experience. We have some other examples of how to use the EEG to kind of create a meditation room experience where the lights and the audio are adjusting based on your EEG signals. This was one of the questions around how do you actually sync with the immersive experience itself and kind of measure behavior. Right now we're showing ways to use the data to kind of control or change the experience itself. And then what Connor had talked about earlier was we're starting to work on, especially when you get the image-based eye tracking as part of it, we're starting to work on how can you kind of automatically tag the physiological data that Galea is collecting with interaction points or events from Unity or from the VR experience.
Pesky rats.
Nice. So Connor has been playing this game quite a lot in the office, so it might take a while for him to get killed by the rats. But you can see he has a pretty good control. And you can change the different parameters that he was talking about earlier to make it more or less sensitive.
Yeah, and what's cool is once I can actually talk while I'm doing it, which might create some false positives, especially because I've turned up my sensitivity.
Mhm.
But that's what we're trying to get to, right? Is where you can do all the other things that you want to do, such as talk and move, without accidentally tripping the false positives, which I think will be a combination of the signal processing that we've done and some machine learning for detecting false positives and excluding that data from the from the events. So yeah,
Nice.
but
No hands.
no hands. So anyway, so that's
Okay.
did we
stop.
show I think we did show Galea Kart last time, right?
I think we did show it. I could, if we have time, I can run another game.
Do you think
I
we
don't
should
know.
show
What do you want?
Synesthesia? Why don't we just do Q&A? Unless people want to see more demos, I guess we could poll everyone.
Do you want to see
Oh,
more
man, I'm not up
demos
to speed
or
on the polling features.
All right, no polling feature. Never mind.
could show synesthesia room briefly if you want to see some EG data, or we can go to Q&A. How many questions?
Q&A.
Joe?
We've
Q&A.
got one vote for Q&A in the chat. I think actually the most common question has been how sensitive is the system to movement. I think that would actually be a good topic for us to tackle with a different kind of video. I don't know if we'll be able to communicate it pretty clearly, but I don't know, Connor, you want to walk around in the background a little bit while the time series is up?
Sure.
Let me pull up the. I could do the spectrogram as well. That's pretty good.
A flurry of votes for demos as well. So maybe after we do a little walk and talk, we can pull up more demos.
Nice. I can hold the cable. The VR.
So, one
one thing that we learned from the ultra cortex, and a disadvantage to the ultra cortex is that, and maybe not everybody listening is familiar with the ultra cortex, but that's the 3D printed EEG headset that goes with our Cyton and our ganglion boards. But the ultra cortex is kind of spring suspended, and it does rattle around. It actually kind of wobbles around on your head. So one technique to removing movement noise is to make sure that, to the best of your ability, the system is pretty rigid and not dynamic relative to your scalp. You want the headset to be, ideally moving with not much inertia or kind of movement relative to the scalp. And so you can see here, as I'm wobbling back and forth, you don't see any large DC shifts in the time series data. And I'm also talking simultaneously, which is, definitely anytime actually the EMG I think is good for showing the sensitivity of movement. So like if I start shaking my head like this, you're going to see a lot of movement noise, right? But it's to be expected if I'm moving my head this much. The movement noise is always going to be an issue, and I think that's an obstacle for EEG. It's not as much of an obstacle for other data types, especially image-based eye tracking and moisture on the skin and stuff like that. But relative to the ultra cortex, the movement noise is substantially lower with Galea, and I think that is as a result of a lot of the learnings of building that headset. But hopefully, you guys can see that I'm moving. Obviously not quickly, but I am moving around, and we're still seeing, pretty decent time series data.
Yeah.
Cool. Yeah, I think this would be a good. We'll have to think about good ways to communicate this, because it's a popular question that's come up. And then, so a lot of people want to see, extra demos. Maybe we can pull up. I guess it's up to you guys. Synesthesia room, or I think the meditation one's good. It's kind of a different type of data that we're using.
Yeah, I'll launch Synesthesia room. That's my favorite one.
Connor, another question, maybe for industry trend question, which, how long do you think it will be before the Quest has, BCI integrated there? How long till BCI and VR go mainstream? Where do you see the industry
Those are two
going?
different questions.
How long do you think before BCI and VR goes mainstream? Where do you see the industry going?
Nice
BCI VR mainstream. I think we're, the next major computing paradigm shift is going to be computers onto our heads. And I think, when we get there, when we have displays, it's already happening. You've got HoloLens, you've got Magic Leap, you've got the Oculus that all have, a CPU that are integrated. That trend is going to continue. And I think that the, computers of the future will be physiologically enabled and highly personalized. So EEG, eye tracking, the same stuff that we have in our smart watches and in our Oura rings and things like that for measuring SpO2, heart rate variability. All of that is either going to be connected, the connected devices to the headset or integrated into a headset. So in the next 5 years, I believe that we'll have mixed reality headsets that are specialized for work, for leisure, for different things like that. But I think, work and then also medical applications. So are going to be some of the areas where we first start to see kind of the widespread adoption of BCI plus AR and VR. So
cool.
But I would say, yeah, it's inevitable. This is just the beginning. This is way clunkier than it's going to look 5 years from now.
Cool. I just pulled up Synesthesia room.
So what data is this using, Eva?
So Synesthesia room is an experience that uses EEG data. In particular, we are using the band power data calculated by the GUI. So the idea for this experience is that the room changes color based on the band power data that we're collecting from you. The colors that the room changes to match the colors in the GUI. So if you can pull up the GUI, actually, it would be helpful. So depending on whether you're making more alpha, theta, beta, the room will be more green, yellow, or blue. And you can use this room as a sort of a neurofeedback training tool to learn how to relax or how to concentrate better. For example, alpha is associated with a relaxed state, and it occurs when you close your eyes. So in this room, whenever you close your eyes and you relax, the color will become green. And also we've mapped different musical notes to the colors. I don't think you guys can hear it in the Zoom right now.
It's in my headset, actually.
Let me try and put it on the speakers.
It might be a little annoying, but hopefully not. But it's pretty cool because if you get used to
Yeah,
it.
we don't hear the audio at the moment.
I'm
Yeah,
gonna
it's in my
try.
headset right now.
Can you hear it now?
Yes.
Okay, so the audio also changes based on the frequencies that your brain is producing. And we added audio so that you can also have some sort of guidance when you're closing your eyes, for example, and you're not able to see the color. So I think you should, right now you have your eyes open, right? Now you just close them. I can see that his alpha is peaking, both because the room is turning greenish, and also I see the GUI, so I can see the spike in alpha. So you can see that the room is green because he is relaxed and he's producing more alpha than the other frequency bands. Nice. There's also a particular note associated with alpha. I don't know if you remember which one it is. But by using this room over time, you're able to tell the difference in the sound as well.
And we're just getting started here. This is a very basic mapping, but we're starting to look at layering sounds and having this kind of these entrainment experiences that help you meditate and generate theta and potentially even delta and deeper states of meditation. But also as we start to train classifiers, we can actually embed neurofeedback loops for various classifiers such as concentration, relaxation, and these different kind of general internal states. So we're starting to work on that now, and hopefully next webinar we can actually present some of the work on the classifiers that we're starting to train within internal research.
Yeah. Even in the early stages, this room has been helpful for me, particularly because I actually struggled to produce alpha, and I've been trying to train my brain to give higher peaks. And I've been jumping into synesthesia room on Fridays for a bit. And the other day we could see the first alpha spike produced my brain ever. So it's been so far, even though it's still a raw thing, it's been helpful.
So proud of you, Ava.
Thank you. I'm proud of
Another popular question. You talk at all about what we've done to shield the electrodes or the electronics from outside noise?
Yes. Let me lower the music actually.
Yeah.
Hear you very well. Do you want me to keep it open?
Oh, that's okay. Yeah, sure. Either one. It's fine.
Nitesh asks whether we've shielded the electrodes themselves from outside noise.
Oh, I see. Let's close it then because it's making a lot of noise.
Yeah. Sorry, Joe. We had the music on.
That's okay.
Back to the GUI.
Back to the GUI. Old faithful.
Okay. Can you repeat the question? You're back to seeing the GUI, right?
Yeah.
I see.
Yeah, Nitesh asks, are the electrodes shielded from outside noise, or he's wondering if the electrodes are shielded in any way, or what we've done on that front.
So yeah, the active electrodes have shielded cabling, and that's the extent of the shielding at this point. While we are exploring more sophisticated shielding options for the beta units and integrating more shielding into the actual enclosures for the device.
Yep. Cool. There's also a question, I think it might have gotten dismissed, but like there's a question around whether is it possible to export raw data, like the raw data that's being saved from Galea, does it have any filtering applied, or is there any filtering applied to the raw data that's being saved, or is it kind of fully unfiltered? And is it possible to add filters to the saved recordings?
So the data that is being saved right now to a CSV file is raw data. So after every time you initialize a session with the GUI, the data gets automatically saved out into I think it's a TXT or a CSV, and that is raw data. When you use the networking widget and you send the data out, you can choose to apply the filters or not apply them. And also the GUI has a functionality where you can replay data that you saved from a previous session. And when you replay that data, you can apply any filters that you want to it, but the filters are not applied to the values in the TXT file itself. It's something we could consider adding though, if it would be helpful. I think it would be easy to save the filtered data in a separate file, for example.
And the other most popular question at the moment, and we might not have this, but there's a question about what is kind of the latency from generation of the signal to detection, and then also being like back to the GUI. So how long from when it happens on the body, until when we're sort of seeing it on the screen and in the data?
That's a good question. I'm gonna quickly open up the timestamp file because I think it would be helpful to answer this. So we've been running some tests to measure the round trip time. Basically, the difference between the device timestamp and the computer timestamp. And let me see. Oh, you took the mouse.
Sorry.
It's okay.
Sometimes I get a little distracted in here.
So right now, I just opened the file on the screen. Our RTT is measuring at around 0.02 seconds.
What does RTT mean?
Round trip time. So we check a few data samples on the device side and on the computer side, and we calculate what is the delay.
That's great.
So is that that in seconds or milliseconds? What is the?
It's 0.02
It's 0.02
seconds.
seconds.
Got it.
23 milliseconds.
It is something that we are working to improve. So it's still work in progress. This is not the final calculation, but it gives you an idea of what the delays are during the session that I'm showing right now.
Cool.
I've
We
got a
are
question.
working
The
through
audience.
most of the questions.
I have a question for the audience. For those of you who are interested in becoming, or coming back for future sessions, what are you all interested in seeing or hearing us talk about for future webinars?
Yeah, just drop that right in the chat if you have anything.
Yes.
Yeah, because there's lots of things that we could do. We could talk about the industrial design and mechanical engineering, the process of going from no headset to prototypes to building a product that quantity hundreds and thousands. We could talk about more about the software stuff and focus on the features that we're implementing on the software side, but also want to know what people want to hear about.
Motor imagery, eye tracking, spatial source localization,
Cool.
the roadmap, and engineering challenges. These are all some of the answers. Thanks, guys.
Great.
Great. That's good feedback.
We're listening.
There's a question about kind of the FPS whether Galea affects sort of the frame, the FPS of the VR experience. We haven't really noticed that, but we haven't done explicit testing of it either. Really, on the kind of computer requirements front, it's the VR that, that's the real requirement. As long as you can run, the Varjo Aero, you'll be able to do everything you want to do with Galea. But we haven't done any kind of FPS benchmarking while everything's running. We might try that in the future.
Yeah.
For what it's worth, running a video call is a much bigger obstacle than running Galea simultaneously.
Right. We're currently running, the webinar, VR, the Galea GUI, and iMotions, I think still maybe, all off of the same computer. So give you some idea.
I think it's also good to mention here that Galea and the VR headset are currently two separate systems. So the VR headset is connected to the computer with its own wire. And Galea is connected to the computer using Wi-Fi. It has its own separate battery. So it's essentially like two separate systems, which we then synchronize in the software side of things.
Okay. There's questions, artifact removal and artifact detection. And yeah, just generally where you see, what games would you make? There are questions actually about whether, can you explain what is wireless and what is wired at the moment?
Yes. So the VR headset at the moment is wired.
It's just the display.
The display. And the Galea part of the system is wireless, and it uses Wi-Fi to communicate with the computer. So all the data coming from all the sensors that we've shown you is getting transmitted via Wi-Fi. Even if you don't have the display plugged in or on, you can still connect Galea to the computer because it's a separate system and it has its own on-off switch and its own battery.
The exception here for when we ship beta will be the eye tracking data. So that the eye tracking, the image-based eye tracking data is integrated into the Aero headset, the Varjo Aero headset. So that data will be making its way to the computer over the tether as well. And then the rest of the physio data will be Wi-Fi through Galea.
Good point. We do have the option of sending data via a wired connection with Galea for those that might need it. But we don't usually use that because the Wi-Fi works well. So we run it in the office with Wi-Fi.
Great.
How is the comfort?
I'm feeling it, like about around the hour mark is where I start to feel discomfort.
He's been wearing it for like an hour and 15 minutes approx.
A little more, because I put it on like
more,
10 minutes prior to the hour.
Almost an hour and a half
Yeah.
of continuous wear.
I feel it, I would say in the last 15 minutes, I've crossed from not thinking about it into thinking about it.
There's a question about whether the HMD causes any interference or feedback in the Galea data.
Nothing substantial at this point that we can tell. Like, as you can see now, we're getting data that's as clean or cleaner than data we see on the Ultra Cortex, and we're running it right next to the display. Right now the Galea system is electrically isolated. There are no conductors going between the display and the Galea device. There might be some electrical noise that we're seeing because the systems are nearby, but for the foreseeable future, we intend for the Galea sensor system to be electrically isolated from the display.
Mm-hmm. We spent some time a few months ago running tests side by side with the display on and off to see if it would cause any interference, and there was nothing noticeable.
Yeah. All right. There's one question about whether there's heart tracking. And the answer is yes. The PPG sensor that's in the forehead can be used to detect heart rate and heart rate variability.
Yeah, right now the widget is just showing the heart rate wave, but we are working to implement different metrics like Connor mentioned at the beginning. Heart rate variability, oxygenation, etc.
And actually, it's good to, we've been running the headset now for an hour and a half, and we've dropped from 91% battery to 78% battery over that time.
It's also been consistent. We haven't had any crashes that required us to restart the device or anything.
Yeah, great showing.
I think we're gonna wrap it up there. I know there's a couple more questions, but we'll keep those in mind for future sessions. Some of them are a bit meatier topics that we can tackle in the last couple minutes. We will be sharing this recording once got to do a little bit of editing and get it downloaded. We'll be putting it up on our YouTube channel where there's some other recordings from previous Galea events. If you are interested in speaking with us about Galea, or you have kind of further questions, if you go to galea.co and click on the inquire button, there's a little form that'll put you in touch with a member of our sales team. So yeah, I mean, thank you for your feedback. Thank you for the ideas for future webinars. We are going to take that into account, and we're also going to follow up with a survey for you all to kind of flesh out some of the feedback you may have already provided. And yeah, keep an eye out for the recording. So thanks for joining, everyone.
Thank you for joining.
A great rest of your week.
Thank you, everybody.
Thank you, everyone.